That's not the evidence of that. So we have here a function that I made up here in green. This is our y equals f of x. And I have labeled here in pink some important points that I want to talk about. And we're going to talk about it in the context of what it means to be a relative maximum or a relative minimum, otherwise known as a local maximum or a local minimum. So there's a lot of language and vocabulary as well as conceptual stuff that's going on here. So different textbooks and different people and different authors will prefer one over the other, relative versus local, but they're interchangeable. I learned calculus a few years ago, and the book that I used it, that I learned it out of, they used relative maximum and relative minimum, so that's what I will use pretty much all the time. But just don't be confused if you see it referred to as a local maximum or a local minimum. So that's one thing. Now, to generalize all of those, that the general class of that includes both relative maximums and relative minimums are local extrema. So that includes both maxima and minima. So one is an extreme point and plural extrema. Just as there's one relative maximum, there could be more than one relative maxima. So the way you plural it is to make it an MA at the end. And likewise, so it's so much language here, so much vocabulary. We just don't want that to get in the way. That's the big thing. You know, if you got to get a level of comfort with the words so that you can get the meaning and the concepts, because it's so new and different that can be a roadblock.
Well, this was calculus, not Latin.
Oh, I know. Well, it's its own language. So you have to become fluent in calculus to do well in calculus. There's no doubt about that. It is a very different language. So what we're saying for a relative maximum is that f has a relative maximum at the ordered pair p comma f of p if f of p is greater than or equal to f of x for all x in some open interval containing p. We're going to talk about what that means. So one thing is, what we sometimes say is a relative maximum is just, you know, there's a whole mountain range out there. A relative maximum is one of the peaks. Okay, it's the tallest part in some little region around it. Now there may be other peaks around it that are bigger. That's okay. It's still a relative maximum. So there may be many relative maximums, many mountaintops in that range. And likewise, a relative minimum is going to be a lowest point. So a relative minimum looks exactly like this, except you're going to replace the f of p greater than or equal to with f of p less than or equal to. Okay, so you can have a mountaintop, which could be rounded or pointed, either one. It could be a valley, a low point, and that's a relative minimum. Now, notice, in the world of AP, a relative max or relative min must be given as an ordered pair. It is a point. If you say that f has a relative maximum at x equals 5, you will not get the point. Okay, it's got to be 5 comma whatever f of 5 is. Okay, so it must be given as an ordered pair, which will get more confusing in the next few days because we're going to talk about an absolute maximum and an absolute minimum, which is the largest y value that the function takes on in whatever its domain is. And those will have to be given as y values, not as ordered pairs. And then it gets confusing. But a relative max or a relative min must be given as an ordered pair, unless specifically directed otherwise. Okay, so let's take a look at this green function, which is doing all kinds of interesting things in all kinds of interesting places. And I want to talk in particular about the ones that are labeled. And is it a relative maximum? Is it a relative minimum? Or is it neither a relative maximum nor a relative minimum? So when we talk about this, I don't want to talk about this a lot today, except I will a little bit briefly here. Now, different textbooks treat endpoints differently. The authors of some textbooks say an endpoint cannot be a relative maximum nor a relative minimum. They only occur on the interior of the function, of the graph of the function. Other textbooks say they can be a relative min and a relative max, in which case we would call that a relative minimum because it's the lowest point in that region around it where it's defined. Okay? Now, the writers of the AP exam understand that there is not universal agreement from authors of textbooks. They will never ask you if an endpoint is a relative min or a relative max, because people will answer differently depending on which textbook they learned from. And that's not what they're trying to test. I learned it a few years ago. The textbook I learned it from said that an endpoint could not be a relative min or a relative max. They must be interior points. Our textbook says they can be a relative min or relative max. I'm not going to make a big deal of it. I don't really care. It's not that important to us. And I will probably forget to think of them as a relative max, relative min, because like I said, I've been doing this for 2 or 3 years and it's pretty ingrained in my head. So I'm trying to get a little more flexible, but we're not going to worry about it. It's not a big deal. Okay? So the other idea is more important. The concept of, is it the highest or lowest point in some region? So when you see what the reason I have B marked here is because what I want you to notice is that if you look at the slopes of the tangent line, there's a place right there where the slope of the tangent line is 0. So this point right here is going to have a derivative that's equal to 0. We're going to come back to that idea in a moment. From our definition, is that a relative maximum or relative minimum or neither? This is where you respond. Neither. Because you can see that if I put that little circle around there, there are points to the left that have smaller y values, so it's not a relative minimum, but there's points to the right that have bigger y values, so it's not the relative maximum. So that is neither a relative minimum nor a relative maximum. Now, when we look at this point here, is that a relative min, relative max, or neither? It's a relative maximum, because it's the largest y value in that little blue circle. That's an open interval containing that point. So that is indeed a relative maximum. Now notice it has a horizontal tangent line right there too. That would mean its derivative is 0. I'm going to come back to that idea. Now looking at D here, relative max, relative min, or neither? Relative minimum. It's the smallest y value in this little circle that contains it. That's the open interval containing that point. Notice it too has a horizontal tangent, so its derivative is 0. How about E? Is that a relative min, relative max, or neither? It's a relative maximum. Does it have a horizontal tangent? No. Its derivative is undefined there. So we've seen that you could be a relative maximum at a place where the first derivative is 0. You could also get a relative maximum at a place where the derivative is undefined, but you could also get a derivative of 0 and not be a relative min nor a relative max either. So the fact that there is a derivative that's 0 or undefined is not going to be enough to conclude there's a relative min or relative max. How about at the point G? Relative min, relative max, neither. Is that the smallest y value for everything that I circled? Yep, so it's a relative min, even though there's a discontinuity there. Okay? So notice there, the derivative would be undefined because there's a discontinuity there. Interesting? How about at H? There's a relative maximum there. Same kind of idea that we saw for this one. This y value here is the largest, and that open interval, that circle of blue that you see there, that too is a relative maximum.
So it's neither because of the bottom.
Say it again.
Is it neither because the other half goes higher? Or no?
Well, but remember, it's just in some little open interval containing this point. So if you look at everything in the blue circle, this is what we mean by an open interval containing h. For all the x values in here, that y value is the biggest. That means it's a relative maximum. It's not claiming it's the biggest mountain in the whole range. It is just a highest point. Okay? How about an I?
Is it an implied maximum? Or it's just happens?
There's no implied anything. It either is or isn't.
It's neither because there's no points on it.
There's not even a point on the curve. Yep. So it's neither relative min nor relative max. It's nothing. It's not even a point on the curve. Yep. It's a vertical, it's an asymptote there. Now here's where it gets really interesting. When you look at this point J, and you look at an open interval containing that, is that a relative min, relative max, or neither? Here's our definition. Is that what I'm trying to show there? I don't know if you can tell now. So it's coming down, it's curved, and then there's a little stretch right in here where it's completely horizontal. So that's supposed to be a little horizontal line segment in there before it bends and goes down more. So at that point right there, if that's in the middle of a horizontal line segment part of the graph, is its y value greater than or equal to all the other y values in that little circle, including it?
Yes.
Greater than or equal to.
So it's
Yep.
both.
Is it less than or equal to all those?
Yeah.
So it's weird. It's both a relative maximum and a relative minimum. In fact, every point along that little horizontal line segment part is both. That's weird. That's more of a trivia question, though. I wouldn't lose any sleep over that one. It's kind of an interesting result of our definition. Now, K is supposed to be at a place where there's a vertical tangent. So you know the derivative is undefined there. Is that a relative min, relative max, or neither? It's neither, right? Because if you take a circle, a little open interval containing that point, there are points on the left that are bigger, there's points on the right that are smaller, so it's neither a relative min nor a relative max.
Did we
Okay.
Skip that.
Pardon me?
Did we skip that?
Did I skip which one?
That.
Oh, I
It's
did.
just like B.
Yeah, in fact, it's supposed to be like B. So there's supposed to be a horizontal tangent right there again. So it comes down, it's decreasing, it goes horizontal for a minute, and then it goes decreasing again. So it's neither. Okay, so these, we have names. When you get a tangent that is zero, and it's just kind of nice to have the words to use. It's not that we're going to make a big deal of it, but when you get a horizontal tangent, but it goes decreasing on one side, decreasing on the other, or a horizontal tangent that's increasing on one side, then increasing again, then that's known as a shelf point. So a shelf point is going to be where the derivative is zero, but it doesn't change sign on either side. It goes positive, positive, or negative, negative. Okay? So the point of this is to say, how do we know where we have a relative min, relative max? How can we find relative max mins? How can we justify, because this is a separate question kind of altogether, that a point is a relative max or min? Because this is a question that regularly appears on AP exam questions. Find a relative min or relative max. Justify. Why is it a relative min? How do you know it's a relative min or relative max? So the point was that we had these places where we saw we had a relative max, relative min. They happened at places where the derivative was zero or the derivative was undefined. What do we have a name for those points. What do we call a point where the derivative is zero or undefined? I have failed. Well, we'll try again. Critical point. Did I mention that? Have I not mentioned it? Maybe it was only in my mind. A critical point, which I will pretty consistently abbreviate CP, because I don't like to take the time to write out critical point, is an X value where f prime of X is equal to 0 or undefined. So a place where the derivative is 0 or undefined is known as a critical point. All of our relative mins and maxes occurred at a critical point. But not all of our critical points were relative mins or relative maxes. So finding where the derivative is 0 or undefined, finding the critical points will give us a way of finding potential relative mins and maxes. And then we're going to have to go further, and how are we going to tell what makes this be a relative max? Sign change in the derivative. It's increasing on one side, decreasing on the other. So the derivative is going to go from positive to negative. What makes this a relative minimum? Decreasing on one side, increasing on the other. This derivative is going to change from negative to positive. You with me? Okay, so this is our first derivative test for relative extrema. Okay, first we're going to find the critical points. Find the CPs. And remember, I'm going to remind you, a critical point is where f prime of X equals 0 or is undefined. So we're going to find them. Then we're going to do a number line for f prime. And we're going to put those critical points on there. CP1, CP2, CP3, oh, no, that's different. Okay? Then what we're going to do is we're going to look at the sign of the derivative in each of those regions. Remember when I was such a nag about doing this when we were doing domains back in AP Prep? An ulterior motive. So suppose, just for the sake of argument, it goes plus, minus, plus, minus. Let's do this. Plus, minus, plus, plus. Even better. Okay? We know from the derivative that it's going to go from increasing to decreasing at this point. That's going to make that be a... Oh, I thought you were right there with me. If the derivative goes from positive to negative at that point, it's going to be a relative. Positive first derivative means it's increasing. Negative first derivative means it's decreasing. If it goes from positive to negative at that point, this must be a relative maximum. So if f prime changes from positive to negative, then I'm going to say CP comma f of CP, because I'm trying to emphasize the fact that relative mins and maxes are ordered pairs, is a relative max. Okay, derivative goes from positive to negative, that's a relative maximum. Is that okay? I need more room up here. Sorry, graph, it took a lot of time and energy, but I'm past that. If f prime changes from negative to positive, then that point CP comma f of CP, right, that x value of the critical point, and then the y coordinate comes from the function, not from the derivative, is a relative minimum. Okay? If the derivative does not change sign, then that is neither a relative min nor a relative max. If f prime does not change sign, the point is neither a relative max nor relative min. Now, to be a shell point, the derivative had to be zero. Remember, critical points can be where the derivative is zero or undefined. So if the derivative is zero and the sign doesn't change around it, that's known as a shelf point. Increasing, zero for a moment, increasing. Decreasing, zero for a moment, decreasing. That'll be a shelf point. But it could also happen at a corner point or a cusp or a discontinuity, and that's not considered a shelf point then. So only if the derivative is also zero there and it doesn't change. That's not a big deal. Don't worry about that. Relative min, relative max, that's a big deal. Worry about that. On the AP exam, they will frequently say, justify your answer. What is an acceptable justification for being a relative min or relative max in the eyes of AP and therefore in the eyes of your math teacher is not that the function changed from increasing to decreasing there. If you say it's a relative max because the function changed from increasing to decreasing there, in their eyes, you have just restated the definition of what it means to be a relative maximum. And you haven't said why that particular point is a relative maximum. Your justification must be one of two things. We'll learn the other one a little bit later. One thing is the first derivative test. You can say there's a relative maximum at that point because the derivative changes from positive to negative there. Period. That's the justification. There's a relative minimum because the derivative changed from negative to positive there. Okay? We'll get another way of doing it too, but I don't think I'm going to get to it today. Okay? All right. Well, we're already ahead of where we were, 5th hour. Let me talk about the second derivative. Question so far? Okay, let me talk about the second derivative and concavity. So if we look at a curve that does something like this. So there are a few different textbooks that have different ways of defining where that's concave up and where it's concave down. So what I want you to see with your eye is that there's a point in there where the function changes from concave down, bowl-shaped down, to concave up, bowl-shaped up. Okay, so that point we're going to call an inflection point. And it's abbreviated, and I wasn't in the room when they decided that. They call it a POI most of the time. Even though they call it an inflection point, they abbreviate it as a point of inflection. So that's where it's going to change from concave down to concave up or concave up to concave down. So our book defines it as this way. So it says, so our book defines it if f double prime of x is positive on an open interval, say A to B, not including the endpoints, then f is concave up on that interval. So they make no bones about it. They're saying it's always going to be concave up or concave down on an open interval. Remember, increasing, decreasing, we include the endpoints unless the function is not defined at an endpoint. But concave up, concave down is always going to be an open interval. And then likewise, if f double prime of x is negative, then it's going to be concave down. I'm not going to rewrite the whole thing. Now, other books define it differently, and so you need to be aware of that any of these is a reasonable description of concave up, concave down. Some books will say that f prime of x is increasing. When the f prime of x is increasing, that's what means that the original function is concave up. And if f prime of x is decreasing, that means that the original function f has a graph that is concave down. Which, I mean, that makes sense, right? Because if f prime is increasing, its derivative, f double prime, would have to be positive. So they mean the same thing. Now, there's a geometric interpretation that every once in a while is really helpful to know. Some books define concave up and concave down in terms of the tangent lines. So if you notice that the tangent lines to the curve where it is concave up all lie, that the curve lies below the tangent lines, or the tangent lines are above the curve. See how the curve lies below all of its tangent lines? That is synonymous with being concave down. Now, when it switches to concave up, you can see that the curve lies above all of its tangent lines. That too is an interpretation or a definition or an understanding of what it means to be concave up and concave down. Okay? Okay. A point C comma f of c where f changes concavity is an inflection point. And different books define this differently as well. So it's got to be a point on the curve. You can't, it may change concavity at a vertical asymptote, but the vertical asymptote is not an inflection point. It's got to be an actual point on the curve. Is that okay? So how are we going to find inflection points? How are we going to find concavity? We do exactly the same thing with the second derivative that we did with the first derivative to find increasing, decreasing, relative, min, relative, max. Okay, we're going to take the second derivative, set it equal to 0. So to determine concavity and find POIs, inflection points. We're going to do the same process we did a minute ago with the first derivative with the second derivative. We're going to find where f double prime of x equals 0 or is undefined. Now everybody agrees that where the first derivative is 0 or undefined, we're going to call a critical point. There's not a universally agreed on term for this. So I'll tell you what I use that some people use, but it's not universal. So I'm going to call these pips for potential inflection points. Okay, so it's going to give us a list of where the second derivative is going to be 0 or undefined. So we'll do our f double prime, and we've got pip number 1 and pip number 2 and pip number 3. And we do like we did before. We look at what's the sign of the derivative. Maybe it goes negative, positive, negative, negative on this one. There's our second derivative. So we know that where the second derivative is negative, it's going to be concave down. Good. So f is concave down from negative infinity to pip 1, because I didn't give that a name. And also from pip 2 to infinity, and so on. Does that make sense? We will have inflection points. So POIs will have inflection points. These must also be given as ordered pairs. And here, like, we don't really care whether it goes from negative, positive, positive, negative. If the second derivative changes sign, That makes it an inflection point. So different than relative min and relative max, where did it change from positive to negative or negative to positive makes a big difference. In the case of an inflection point, it doesn't. So we'll have a point of inflection at whatever that pip number 1 was, and f of pip 1 is going to be an inflection point. Why? Because the second derivative changes sign. So our justification here, we don't really care how it changed, just that it did, is going to be because f double prime changes sign there. That's what you're going to have to say for the justification. Does that make sense? I haven't yet talked about the second derivative test for relative mins and relative maxes. I'm going to do it very briefly, but you may want to look at the supplemental video. I haven't worked an example yet, but I will next time. I'm going to do some more graphing examples, because ultimately I want you to be able to take a function, get all the information from its first derivative, where is it increasing, where is it decreasing, where there's relative mins, where there's relative max, get the second derivative, where's it concave up, concave down, find the inflection points, use all that to draw a graph. So here's a very, very brief second derivative test for relative extrema. Okay, so there's a second way we can justify or find a relative min and relative max. If f prime of x is equal to 0 and, now there's a couple things we can look at. So one thing is, if f, let me say f prime of c, so I'm going to pick a particular value. So if f prime of c is equal to 0 and f double prime of c is positive, that combination, 0 first derivative gives us a horizontal tangent. F double prime positive means it's concave up. So a point where you have a 0 derivative and it's concave up, that's going to be a relative minimum. If f double prime of c is negative, at the same place where the first derivative was 0, that means you got a horizontal tangent and it's concave down. That combination is going to make it a relative max. If the second derivative is 0 as well, we know nothing. Could be a relative min, could be a relative max, it could be neither one. And I will talk about some reasons why that is. So that's just inconclusive, we can't tell. Thank you for your patience. We'll do more on this tomorrow.